Welcome back to the deep dive. Usually when you look at the physical world around us, like a massive skyscraper or a newly paved highway, maybe a sprawling airport terminal, you just see the finished product, right?
Yeah, exactly. You see the concrete and the glass and the steel.
Right. It feels solid. It feels permanent, almost like it just, I don't know, sprouted from the earth that way. But if you could somehow look past that physical layer, if you could put on a pair of glasses that showed you the secret matrix code running underneath our civilization, you wouldn't see bricks and mortar. You would see a spreadsheet.
A very, very long, incredibly specific spreadsheet. I mean, it's essentially the ultimate blueprint of human effort.
Okay, let's unpack this because for today's deep dive, you, our listener, are getting a pair of those glasses. Our mission today is to take this document, which frankly looks like an impossibly dry, dense list of construction line items, and reveal it as the hidden logic of how mega projects actually come to life.
Yeah, and the document we are looking at is, it's called the FIDIC Red Book Schedules, specifically the civil unit rates.
Which sounds thrilling, I know.
Right, it sounds super dry. But FIDIC is basically the International Federation of Consulting Engineers. Their Red Book is the globally recognized standard rule book for huge construction contracts.
Like massive international mega projects.
Exactly. And it relies on a WBS, a work breakdown structure, which is, essentially the master checklist of the universe for a project, because to build civilization on a macro scale, you can't just tell a contractor, hey, go build a bridge.
Right. They need a few more details than that.
Just a few.
Yes.
You have to define legally and financially the exact cost of every single grain of sand, every hour of labor, every potential physical risk. So when you see the unit rates priced out in euros in this document, it acts as a like a universal financial translator.
It dictates how the chaos of nature is transformed into human order.
Yeah, perfectly put.
And, well, before you can build that order, you have to dismantle whatever was there first. It's the ultimate blank slate.
The demolition phase.
Right, WBS category 600. And rather than just, rolling in a bulldozer and pushing some dirt around, the schedule shows this hyper-granular approach to neutralizing the existing environment. Like, it starts with site clearance, and it prices trees not just by the fact that they are trees, but by their exact physical dimensions.
Yeah, the schedule breaks down the labor required in these precise increments. So it lists a baseline rate for removing a tree with a girth of 500 millimeters up to 1 meter.
Okay.
Then it scales up like 1 to 2 meters, moving incrementally all the way to a specific line item for a tree girth exceeding 5 meters.
Exceeding 5 meters. I mean, imagine standing in front of a tree that massive and knowing there is a predetermined euro value attached to the physical labor of cutting it down, grubbing up the stump, pulling out the massive root system.
Wait, look it all away.
Right, carting it away and backfilling the hole so the ground is perfectly flat again. It feels like a surgeon meticulously prepping an operating table. You're clearing the ecosystem so the real work can begin.
And that surgical prep also involves managing invisible forces before you ever even dig a foundation.
Like what?
Well, WBS 601 covers general earthworks, and it has these incredibly detailed pricing models for dewatering systems. Because, if you were digging in an area with a high water table, the earth is essentially a giant sponge.
Oh, right.
You have to squeeze the water out and hold it back, or your trench just turns into a lake.
So what does that actually look like on the ground? Like, how do you price holding back groundwater?
It depends entirely on the depth and the physics of the water pressure. The document prices a shallow dewatering system, which reduces the water level by 1,000 millimeters using headers spaced at 1,500 millimeter centers.
Okay, so that's for shallow water.
Right. But if you need to reduce the water by more than 1,000 millimeters, it requires a deep system. So the well points are placed much tighter together, like at 1,000 millimeter centers, with significantly more pumping power.
Wow.
You are literally paying for the mechanical force required to hold back the ocean or the local aquifer, just so your operating table stays bone dry.
And once it's dry, you have to actually dig. And this is where I need to push back a little bit on the sheer number of line items, because the document gets almost obsessive here.
It really does.
When it comes to excavating rock, they break the depths down layer by layer. There's a unit rate for digging rock at a maximum depth not exceeding 0.25 meters, then 0.25 to 0.5 meters.
Half a meter to 1 meter?
Yes. It marches down incrementally all the way to rock, requiring blasting at depths exceeding 15 meters. So my question is, why not just charge a flat rate for digging rock? I mean, rock is rock, isn't it? If I'm paying a contractor per cubic meter, why does the depth dictate dozens of different price tiers?
What's fascinating here is that in the world of mega construction, risk is money.
Okay.
The deeper you go, the more the fundamental physics of the job change entirely. Like digging rock at a quarter of a meter below the surface. You can use standard heavy machinery, like an excavator with a breaker
Well,
attached
you
to
can
it.
just smash it.
Exactly. It's predictable. You can see what you are doing. But once you go past 5 meters, 10 meters, and especially exceeding 15 meters underground, the geology becomes incredibly unpredictable.
Because the pressure changes. Or is it that the density of the Earth shifts?
Both. Plus, you run a much higher risk of hitting unexpected subterranean structures or sudden shifts in the rock's hardness. The structural integrity of your excavation walls becomes this massive safety hazard that requires way more support.
Oh, I hadn't thought of the walls caving in.
Right, and at those extreme depths, standard machinery might not fit, or it might not have the leverage. You often need specialized blasting equipment.
Which means explosives.
Explosives experts, safety perimeters, vibration monitoring for nearby structures. The schedule forces the contractor to account for that escalating unknown risk up front. By forcing the pricing into these micro increments, the contract acknowledges that removing a cubic meter of rock at the surface is fundamentally a different physical and financial undertaking than blowing up a cubic meter of rock 15 meters underground in the dark.
That makes a ton of sense. You are pricing the uncertainty of the Earth itself.
Exactly.
So the ground is cleared, the water is held back, and this massive, heavily calculated hole has been blasted out of the rock. Now, the physics problem flips.
Just to build it back up.
Right, you have to fill that void with something stronger than the Earth you just removed. Which brings us to WBS 602 and the 603, the foundation.
Mm-hmm.
And looking at the concrete specifications are really something. Concrete is never just concrete.
Oh, absolutely not. The chemistry and the engineering hidden in these line items are staggering. The schedule specifies the exact chemical makeup and strength, starting from a basic class 15 up to a heavy-duty class 60 GB.
Grade SS60, right. But here's where it gets really interesting. It's the high-tech reinforcements hidden in the text. Like, I was expecting to just see regular steel rebar, which is, standard for concrete.
Sure.
But then the document starts listing line items for fibrillated polypropylene fibers.
Yeah, those are synthetic, plastic-like fibers. You mix them directly into the wet concrete before it's even poured.
Wait, how does that actually work? Does it replace the steel?
In many applications, yeah.
Yeah.
Instead of laying down a heavy, cumbersome grid of steel wire mesh, you mix millions of these tiny fibers into the cement truck.
That's crazy.
When the concrete cures and hardens, those fibers act like a microscopic three-dimensional web holding the concrete together from the inside out. It prevents the concrete from shrinking and cracking as it dries, and crucially, it requires 0 labor hours to assemble compared to cutting and tying steel mesh.
That is wild. And it gets even more advanced. My absolute favorite line item in the concrete section is the carbon fiber reinforced polymer strengthening strip, the Sika Carbo DUR.
Oh yeah, that's high-end structural engineering.
The document specifically prices out applying these 1.2 millimeter and 1.4 millimeter thick carbon fiber strips bonded directly to the surface of the concrete with epoxy resin. To use an analogy, building with standard steel rebar is like putting bones inside the concrete to give it structure. But bonding these carbon fiber strips to the outside is like putting the concrete in an ultra-tight, unbreakable exoskeleton. Yeah. It distributes the load and the weight entirely differently, giving it incredible strength without adding mass, like upgrading from a heavy iron broadsword to a high-tech scalpel.
And that completely alters the economic nature of the build. Because those carbon fiber strips cost significantly more in raw materials. They are priced per meter in the schedule, but they require completely different labor and equipment compared to, hauling and hoisting tons of solid steel.
So it's a trade-off.
Exactly. You trade material costs for speed and structural efficiency. And the schedule goes just as deep on the temporary structures used to pour that concrete. The
molds, essentially. The wooden or metal framing you pour the wet concrete into so it holds its shape while it dries.
Yeah, and the schedule meticulously separates this formwork by the desired finish and the physical plane. You have separate unit rates for a rough finish versus a fair finish.
Yeah.
And then it breaks those down further by horizontal planes, sloping planes, vertical planes, and battered planes.
So I have to ask, what exactly is a battered plane in this context? Because it sounds like concrete that's been in a fight.
It does, right?
Yeah.
But no, a battered plane is a wall with a receding slope. meaning it leans backward as it goes up.
Oh, like a retaining wall.
Exactly. Often used to hold back earth. So if you are pouring a battered wall and you require a fair finish, meaning a perfectly smooth, architecturally pleasing surface with no visible seams or imperfections, the mathematical precision required is exponentially higher than pouring a rough horizontal slab that will just, be buried underground anyway.
Because the mold has to be absolutely flawless.
Flawless, and constructed from higher grade materials like specially coated plywood or steel panels that won't leave a wood grain imprint. The joints have to be sealed perfectly so no wet cement bleeds out and creates a ridge. The labor time to assemble that flawless mold, the chemical release agents used so the mold doesn't stick, the care taken during the actual pouring, all of that is dictated by the phrase fair finish.
So every time I walk through an underground parking garage or like a modern building lobby and I see a perfectly smooth, sloping concrete pillar, I should be thinking about the fair finish, battered, plain line item.
You really should.
That smooth texture isn't just an aesthetic quirk, it's a specific labor cost and material upgrade that someone calculated down to the euro.
Every single aesthetic and structural choice is quantified.
Okay, so we have our high-tech, fiber-reinforced concrete foundation poured into mathematically perfect molds. But a mega project isn't just a solid block of stone. It needs systems to run through it, to supply it with water and power.
Infrastructure.
Right. And it needs to be anchored deep into the bedrock so it doesn't tip over. This brings us to WBS 605 and 606, the hidden underground world of pipes and piles, what I like to think of as the invisible nervous system of the project.
Yeah, looking at the pipework specifications, it is a masterclass in how materials science dictates project planning.
The array of materials is dizzying. The document lists GRE, which is glass reinforced epoxy HDTE, meaning high density polyethylene.
Standard PVC.
Yeah, and galvanized carbon steel. And just like the rock excavation we talked about earlier, the trenching required to lay these pipes is highly specific. It starts with trenches not exceeding 1.5 meters deep.
Then 1.5 to 2 meters.
2 to 2.5 meters, and 2.5 to 3 meters deep. And here I go again, but I really have to challenge the logic of this spreadsheet. Why are there entirely separate line items and dramatically different price points for laying a 200 millimeter HDPE pipe in a trench at 1.5 meters versus laying that exact same piece of plastic pipe into a trench at 2.5 meters?
It seems like it should be the same, right?
Yeah, the pipe doesn't change. Isn't it just the same material sitting at the bottom of a slightly deeper hole?
If we connect this to the bigger picture, it is never just a slightly deeper hole. When you dig a trench for a pipe, especially as you approach that 3-meter mark, you are fighting a massive war against gravity and earth mechanics.
Okay, how so?
Well, a 1.5-meter trench might be relatively stable on its own, depending on how cohesive the soil is. But a 3-meter trench, which is nearly 10 feet deep, is a potential death trap.
Because the walls want to cave in on whatever's at the bottom.
And gravity is unforgiving. A single cubic meter of soil can weigh as much as a standard car. So if a 3-meter trench collapses on a worker who is down there laying that pipe, it is instantly catastrophic.
Oh my God.
Yeah, so as that trench gets deeper, you aren't just paying for an excavator to scoop out more dirt. You're paying for exponentially more complex shoring systems.
Like walls to hold up the dirt walls.
Exactly. Hydraulic struts and steel trench boxes that actively push against the dirt walls to hold them back. You are paying for more intense dewatering to keep the bottom stable. You're paying for much slower, more meticulous safety protocols, including ladders placed every few meters and spotters on the surface.
Right.
The piece of HDPE pipe is identical, yes. But the environment you are forcing human beings to work in to install that pipe becomes vastly more dangerous. It requires massive mechanical intervention just to keep it safe.
Wow. So the price increase isn't about the pipe at all. It's the cost of keeping millions of pounds of earth at bay while the pipe goes in.
Exactly.
That perfectly transitions into the other half of this invisible nervous system, the paneling. Because if you think holding back a trench wall is fighting gravity, piling is where we see the true scale of the forces at work in modern construction. WBS 608.
Yeah, the piling specifications reveal the immense hidden anchors that keep our world upright. The document lists isolated steel piles, and it prices both the pre-boring and the piles themselves by their mass.
And the mass is staggering. They start with light piles under 15 kilograms per meter, but the scale goes all the way up to massive steel piles that weigh between 500 kilograms and 1 metric ton per meter.
Just massive amounts of steel.
Just 1 meter of this steel pillar weighs as much as a small car, and they are driving dozens of meters of this into the earth. But the part that really caught my eye was the testing. They don't just hammer these massive steel columns into the ground and hope they hold the building up.
The liability of hoping for the best is a risk no one can afford. The schedule mandates and prices out rigorous pile tests with maintained loading for various reactions.
And again, the scale is wild. The tests start at a required load not exceeding 100 tons, which is heavy,
Very heavy.
but it scales up 200 tons, 400 tons, 800 tons, all the way to a line item for a test load between 800 and 1,000 metric tons. To give you, the listener, an idea of what that means, 1,000 metric tons is roughly the equivalent of stacking two fully loaded 747 jumbo jets on top of a single steel pillar no wider than a manhole cover. How in the world do they even test that on a construction site?
It requires an incredible mechanical setup. To simulate the weight of the future building, they usually build a massive steel reaction frame over the pile.
Okay.
Then they either pile hundreds of tons of dead weight, like massive concrete blocks on top of the frame, or they anchor the frame into adjacent piles.
So it can't move.
Right. Finally, they place enormous hydraulic jacks between the frame and the test pile. The jacks push down on the pile with 1,000 tons of force, while highly sensitive gauges measure if the pile sinks into the earth by even a millimeter.
That is just brilliant.
It's vital context for how we experience the built environment. Like when we stand on the top floor of a skyscraper, we feel weightless. The building feels completely static. We don't feel the structure straining against the earth.
Right, you just feel like you're in a room.
But those 1,000-ton pile tests represent the immense invisible forces constantly required to keep a modern structure upright against wind shear, gravity, and potential seismic activity. The contractor has to physically prove, through the sheer force of hydraulic jacks, that the earth and the steel can handle the load. And this document dictates exactly how much they get paid to engineer that proof.
It's incredible to think about the sheer physics of it all happening right beneath our feet. But eventually, all this deep infrastructure, the earthworks, the deep trenches, the massive steel piles that has to emerge above ground,
It does.
it has to become a surface that human beings actually walk on, drive on, and interact with. And that's where the schedule shifts in a really fascinating way, moving from the invisible to the visible, Category 609.
Yeah, the document transitions into roads and pavings, moving us from the realm of pure geological physics into the realm of human behavior.
The schedule details the road subbases, the granular material, the asphalt concrete wearing courses, again, all measured perfectly by thickness, from 30 millimeters up to 300 millimeters. But the part that really stopped me in my tracks was the signage and ancillary section.
The signage requirements paint a very distinct, almost alarming picture of the environment these mega projects create.
It reads less like a construction schedule and more like a script for a disaster movie waiting to happen.
It really does.
The document lists exact, highly specific warning signs that the contractor must supply, install, and price out. Things like danger flammable liquid, danger confined space, hearing protection must be worn.
Standard stuff, but a lot of it.
Yeah, but then there's a line item that is incredibly specific. It says, danger, no naked flames, no smoking, no matches, no mobile phones, no cameras.
It highlights a highly restrictive, highly volatile environment.
So what does this all mean? To me, it shows that you can calculate the exact compressive strength of Class 60 concrete. You can perfectly measure a 1,000-ton hydraulic load on a steel pile. But the moment you introduce actual human beings to the site, human error becomes the ultimate variable.
Absolutely.
The construction site is this living, breathing ecosystem where a single dropped match or a distracted worker looking at a mobile phone next to a fuel line can undo millions of euros of perfectly calculated engineering in an instant.
This raises an important question. How do you calculate the cost of safety?
Right. How do you even put a price on that?
Well, while the earthworks and the concrete pouring deal with the rigid laws of physics, the signage deals with the laws of liability and psychology. Every single sign on that list represents a specific, documented hazard that the contractor must legally and financially mitigate.
Oh, I see.
If they fail to post the danger confined space sign near one of those 3-meter deep trenches we talked about, and a worker enters without proper ventilation and gets hurt, the legal ramifications dwarf the cost of the entire trenching operation.
So the euro rate attached to that sign isn't just for a piece of metal and some reflective paint.
No, not at all.
It is the price of a legal shield. It's the cost of behavioral engineering.
You are paying a specific unit rate to modify human behavior, trying to protect both the physical asset you are building and the fragile human lives building it. It is risk management translated into a physical object.
That is a profound way to look at a spreadsheet. We've gone on quite a journey today through this single document. I mean, we started by calculating the exact physical cost of clearing a 5-meter wide tree stump from the earth.
We did.
We've mixed microscopic plastic webs into our concrete and strapped carbon fiber exoskeletons to the foundation. We've buried high-density polyethylene pipes 10 feet underground, fighting the crushing weight of gravity with hydraulic shoring.
We've simulated the weight of 2 jumbo jets on a single steel pile.
And finally, we've hung a no mobile phone sign to try and engineer human behavior so the whole thing doesn't go up in flames.
It is the complete life cycle of a project, reduced to its core economic, physical, and psychological components.
And knowing all of this completely changes how you see the world. The next time you, our listener, are walking down the street or walking through a modern city or driving across a paved road, I want you to remember that you aren't just walking on asphalt and concrete.
You are moving through a living, breathing spreadsheet.
Every curb, every pipe hidden beneath the sewer grate, every warning sign on a fence has a hidden tag on it. It all has an exact work breakdown structure code and a highly specific labor and material cost attached to it.
Nothing in the built environment is accidental. Everything has been accounted for, negotiated, and priced out to the millimeter.
Everything. Which leaves me with a final thought for you to mull over. If every single physical object in our built environment has a specific cost, a hidden tag, and a calculated risk attached to it, what would it look like if we applied this unit rate logic to our own lives? Right. How much labor and material goes into building our own daily routines, our habits, our personal foundations? Are we pouring our energy into the equivalent of rough form work? Or are we taking the time to build a fair finish? Are we accounting for the deep, invisible trenching and the heavy load testing it takes to build our own resilience? Just like the matrix code of the city we talked about at the very beginning, maybe the most complex structures we are building aren't made of steel and concrete at all.
If you're interested in the templates, please visit our shop. The link is in the description.
Thanks for watching. Please subscribe and see next time.